All right, good morning, everybody. Welcome to our talk. So we're going to be talking about tracing the path of a row through a GPU-enabled query engine on the Grace-Blackwell architecture. I'm Tom Graves. I work at NVIDIA on the Spark team. I've been there about 6 years. Prior to that, I worked at Yahoo/Verizon on their big data platform team, doing all sorts of big data stuff: Hadoop, MapReduce, Yarn, Storm, Kafka, Spark. I've been doing Spark stuff a long time. Been a Apache committer and PMC member since about 2013. So I'm going to hand it over to my colleague who will introduce himself and then get us started.
Thank you, Tom. My name is Clemens Lutz. I'm also at NVIDIA. I'm a senior developer technology engineer working on database stuff. Before that, I was a PhD student at TU Berlin. Also working on very similar topics. Back then, that was on a Power 9 Volta platform, where I was working also with NVLink between these two platforms. Was publishing at Sigmod and some of the other database conferences back in the day. With that, I'll dive right in. So the premise for today's talk is that you all are interested in processing large amounts of data. And these data can be very big, in the hundreds of gigabytes, terabytes, maybe upwards. And typically, GPUs would be a very good architecture to process data. Because GPUs, from the hardware architecture perspective, are very highly data parallel. They have massive amounts of memory bandwidth in the terabytes per second. And they also feature a very high compute throughput to match. The question is now, how can we actually scale to these large amounts of data that interest us using this kind of GPU architecture? And there are some systems out there that can do data processing on GPUs, and the typical architecture for such a GPU-enabled database management system would look something like this, where we have our big quantity of data, and we're storing that alongside the CPU, because that's where we have the space to store it, either in some terabytes of CPU memory or on the disk, also alongside the CPU. But then during query execution, the system will transfer that data ad hoc to the GPU, where it then actually performs the execution of the individual operators. And the underlying assumption being that we don't have enough GPU memory to store all of this data in GPU memory. Of course, we can now also say we don't just do this on a single GPU, but we scale it out to many GPUs. Maybe we also use the CPU alongside the GPUs to do that scale-up processing. And then we need to connect these devices with some kind of interconnect fabric, preferably something that's fast enough to actually saturate these GPUs. And I want to convince you in this talk that in both of these scenarios, so when we are running on just a single device or a single node, but also in the scale-out case, Grace-Blackwell offers a unique advantage in terms of how fast we can execute queries on large data sets. So going forward in this talk, our agenda is going to be that we're first going to look briefly at the Grace-Blackwell hardware architecture. And after that, we're going to look at some measurement results and the architecture of a prototype query engine that we're building at NVIDIA to showcase how to use these kinds of Grace-Blackwell systems. And the results that I'm going to be showing is going to be on a single GPU. But of course, we can also scale out using Grace-Blackwell to a cluster setup. And that's what Tom is going to show you with the RAPIDS Accelerator for Apache Spark. And he will also then show you even bigger data sets than I can show on a single GPU on the cluster setup. So let's dive into the Grace-Blackwell architecture. Just to give a very brief overview of how a node looks like in Grace-Blackwell, a node will usually consist of 2 Blackwell GPUs, and these are connected to each other with NVLink. And they're also connected with NVLink to a Grace CPU. So this is an in-house design also from NVIDIA. All of these processors have some local memory attached, and the three processors also are within a cache coherence domain. That means we can basically take a pointer on any of these CPUs or GPUs and dereference that pointer to anywhere in that coherence domain and get that data. And the hardware will take care of fetching it for us, which is very nice when we're writing software on these platforms. But for the performance aspect, I want to highlight three key features of Grace-Blackwell. The first being that these Blackwell GPUs have a very high amount of GPU memory. So we're talking now about 192 gigabytes per Blackwell GPU, which is significantly higher than previous GPU architectures had. So for Ampere, Hopper, we're usually talking about 80 gigabytes. So this is more than twice the capacity. And that means we can fit larger data directly with the GPU. The second advantage is the C2C interconnect. So this is NVLink core-to-core between the Blackwell GPUs and the Grace CPU. And that gives us much higher bandwidth than competing technologies. So we're talking about 450 gigabytes per second in total. And that's compared to something like 128 gigabytes per second for PCI Express 5. So this is now 4 times the bandwidth of the competing technology. And a third key advantage for data processing is that Blackwell GPUs have on their die a hardware component for decompression. So we call this the decompress engine, and that is capable of decompressing data streams for heavyweight compression algorithms in parallel at up to 600 gigabytes per second of output throughput. And so, yeah, that's a pretty high bandwidth, and it supports several different popular compression formats. So these include Snappy, LZ4, gzip deflate, and some others as well. So these three key advantages for Grace-Blackwell make it, for us, very interesting to build systems, database management systems for this platform. And that's what I want to show you by tracing the path of a row to familiarize ourselves with this prototype query engine that we're building. So just taking a very simple example to give an outline of how the system processes a query. This is just a very simple select statement that takes a table, executes a predicate on that table, and then does a group by on a key, and does a summation of another column. And what this might look like in the execution plan in our query execution engine is that we're taking the data, we're feeding that to a read operator that passes its data to a filter. The filter then passes its data to the aggregation, which then, and finally we write out that result to a result table. But let's take a look at the single row in the output and see how that comes to be. So that row is going to be written to the output table by the write, but that write takes it from a hash table. So that row is originating from a single entry in that hash table, which is being created by our aggregate operator. So this aggregate is summing up multiple columns from its input and creating that row in the hash table. And the aggregate is taking its input from the filter, which is filtering out some columns from the read. Right? So this is how data is flowing through the system. But the interesting part now is when we look at just some ballpark estimates for what kind of performance we might expect for these individual operators, we're going to see that the read is maybe 100 gigabytes per second in that ballpark, where the other operators are going to be much faster. Right? So that means our potential bottleneck is usually going to be that read operator in our system. And that means we need to take a much closer look at that read. And that's what we're going to do now. So I want to show you some actual benchmark results as we go along. This is going to be using the NDSH benchmark from NVIDIA. NDSH is a derivative of the well-known TPCH benchmark used in the industry. And what we're going to be doing is executing the same 22 queries from TPCH and executing those in memory in our query engine, and then computing a geomean throughput over these 22 queries. But I also want to emphasize that because we're not executing the full TPCH benchmark, these results are obviously not comparable to results published on the TPC website, right? So these are just these 22 queries being executed individually. I'm going to be showing these benchmark numbers on two platforms that are being hidden here by the transcript. So I'm just going to read this out loud. So the one is our prototype query engine that we've built in-house. That's running on a GB200 system, which is a Grace-Blackwell system that has 480 gigabytes of CPU memory attached to it. And it's going to be running on a single GPU. I'm going to be comparing these results to a state-of-the-art CPU baseline. That's going to be DuckDB in the most recent version, running on a single CPU, namely an Intel Emerald RAPIDS platform, which has a terabyte of memory attached. All right, let's dive into these numbers. And so just looking at this read operator again, what's going on with the read? Well, we can now, due to this advantage of the Grace-Blackwell architecture, store a significant amount of data directly in GPU memory. And that means our read operator is just going to take that data, project out the columns that we actually need, because we're storing it in a columnar format, and then feeding that data into the next operator, which is our filter. So the read itself isn't doing that much at this point. And when we look at the measurements, what we can see here is, for the audience in the back, the dark green bar here is an A100 GPU, which is an older generation, and we can fit scale factor 80 directly into GPU memory on that GPU. So we can execute some data in GPU memory also for these kinds of GPUs. And of course, we can do the very same thing on a Grace-Blackwell, right? We can just fit scale factor 80 in GPU memory there. And both of these GPUs are going to get some pretty good numbers compared to a state-of-the-art baseline, because GPUs have very high memory bandwidth. However, the interesting part is now when we start scaling up our data to larger and larger sizes as we go. So here, we can already scale up to scale factor 200, which is more than a doubling in GPU memory on Grace-Blackwell. And that kind of data isn't going to fit on these older GPUs. It will execute on the CPU as well, just with lower performance. But we're not happy yet. We want to scale higher. So let's scale to a larger size. And we can do that by using the second advantage of the Grace-Blackwell platform, which is this NVLink C2C interconnect to the CPU, which means we can now store the data in CPU memory, meaning we have more of that and can scale to a larger scale factor. In this case, it's going to be scale factor 500. And what the read operator is now doing is it's taking that data in CPU memory, projecting out the columns, which isn't a lot of work. This is just operating on some metadata. So we're not actually touching the data at this point. But then we're going to transfer those columns that we need for query execution across the interconnect to the GPU, store them temporarily in GPU memory, and execute the query from there. And the interesting part here is when we compare the dark green bar, which is now also a Blackwell GPU, just connected with PCI Express instead of NVLink, we're getting 3 times the amount of performance compared to this other Blackwell GPU using the Grace-Blackwell platform. Both of these are getting better performance than our state-of-the-art CPU baseline still. Now at scale factor 500, but we can scale higher. So let's go to the third advantage of Grace-Blackwell, which is the decompress engine. With the decompress engine, we can store our data in a compressed format, which means we can store even more memory or even more data in memory alongside the CPU. And our read operator is going to look slightly different now. So what we're doing is we're taking our projected columns and transferring that data again, but this time it's compressed data that we're transferring. And on the GPU, we're going to use our hardware decompress engine to decompress that data, and then we can access it in a decompressed format from the other operators. So it just adds an additional step there as well. And this time, I'm going to be comparing a Grace-Blackwell system to itself, just in two different software configurations. The one being that we're using a software-based decompression on the Blackwell GPU, which is the dark green bar. The light green bar is using the hardware decompress engine. Now, we're scaling now from scale factor 500 previously to scale factor 1000 in CPU memory. And we're getting twice the performance when using the hardware decompression versus the software-based decompression. And both of these scenarios are going to be faster than our baseline, which is now also using compression because we couldn't even fit the scale factor into 1 terabyte of memory. I do want to point out, though, that these numbers, especially for the decompression engine, I just recently got them, like yesterday. So these are very, very early numbers. We're still working to improve them, and you can expect better performance going forward as well in future presentations. Before I hand over to Tom, I just want to wrap up my part of the talk and have some conclusions here. So the first being that GPUs as a hardware architecture are generally well suited to compute data, and specifically have them embedded in database management systems. That's a win for us. But there was always this challenge of accessing large amounts of data, and this is where really Grace-Blackwell shines, because we're now getting 3 advantages of that platform that we can take advantage of in our system, which is the larger memory capacity, getting us a scale factor 200 right in GPU memory. Then the Grace-Blackwell NVLink, which gets us to 500, scale factor 500, using the CPU memory with a very high performance. And then the decompress engine is the third advantage, where we can then store even larger scale factors also in memory without even having to fall back to disk and still get really good performance and scalability right there. So, taken together, these 3 features really enable us to build these high-performance query engines using GPUs and get some really nice numbers there. With that, I'm going to hand over to Tom. He's going to show you scaling up to even bigger data.
Thank you, Clemens. So I'm going to go over RAPIDS Accelerator for Apache Spark. And so this is how we can scale to larger data, like Clemens mentioned. So what is the RAPIDS Accelerator for Apache Spark? So this is a plugin for Apache Spark that basically accelerates data processing using the GPU. So our main goals here when we started this project was to make it as seamless as possible for users. So we didn't want them to have to make code changes, and we wanted to go to where they were at. So lots of people have different versions of Spark, so we wanted them to be able to use our plugin on any of the versions, or as many as possible. So how did we accomplish this? So we ended up having to make changes to Spark to allow this. So we made some changes for columnar processing. We added a plug-in point into the planner to allow us to plug in to be able to change operations to run on the GPU. And then we also added GPU scheduling to Spark. Really, it's resource aware, but GPU is one of the resources you can schedule. So that allowed us basically to just create a jar that you just download the jar, turn on a config, and then you're off and running. So you can run and use the RAPIDS Accelerator to accelerate your jobs. So in this picture here, we have our data analytics applications. So if you're running Apache Spark, and the other requirement is you have to be using either the SQL or the data frame API. So those are the ones that are going through the Catalyst, Planner, and Optimizer. And as long as you're using those, we can seamlessly transition your jobs to run on the GPU when needed, or when possible. So as this picture is kind of showing, we support various of the platforms and CSPs, so Databricks, AWS, GCP, will run on any of those. Under the covers, the Spark plugin actually uses the library called RAPIDS, which is another NVIDIA library. And within there, it has a component called cuDF, which is CUDA data frames. And that's the layer that actually knows how to do the ETL operations on the GPU. So it's got the C++ and CUDA code. So we end up using that. All right, so to look a little bit closer at a query. So here's a group by aggregate. And we have both the data frame and SQL API. And so what does Spark do with this? So when you execute this, it creates a data frame, and then it'll go through the planner, right? So it creates a logical plan first, and then it'll do optimizations on that plan, and then you'll get a physical plan out. This physical plan is what would actually execute. So if we look at that in more detail, here's the CPU version, right? So you have hash aggregates, projects, broadcast hash join, and so forth. And so that's the code that would actually execute and produce your results. So how does that look with the Spark RAPIDS Accelerator? So we have no code changes over here. So code's exactly the same. But when you get to that physical plan stage, it actually iterates, and that's where our plugin comes in. And so we go through and we look at each of the operations that you're performing and determine if we can replace it and do it on the GPU. And if we can, we'll replace it. And if there's any transitions needed, so the CPU is running in row format, GPU is running in columnar. So if we need to do any transitions, we'll insert those for you as well. And all this happens without you having to do anything. So here's an example of the GPU plan. You'll see the whole thing is actually running on the GPU. And so where it was a CPU hash aggregate, we now have a GPU hash aggregate and a GPU project and so forth. And so again, the user didn't change any code here, and it will just run on the GPU when possible. If there's something we don't support on the GPU yet, it'll just keep the CPU operation there and deal with the transitions for you. Okay, so let's look at this actually running on Grace-Blackwell. And so we're using NDS here, which is a TPC-DS-like benchmark. So it's similar to the NDS-H, but it's TPC-DS based. So in our setup here, we had 8 CPU nodes. They're Emerald Rapids CPUs with 56 cores, 112 threads. There's 2 sockets on each node. We had 2 terabytes of host memory, 400 gigabits per second network, and 8 NVMEs set up in RAID 0. On the GPU side, we had 8 Grace-Blackwells. So the Grace has 72 cores. The Blackwell, or we had 1 B200 per executor, basically, per node. 2 terabytes of memory, 400 gigabits per second on the network, and 8 NVMEs in RAID 0 as well. For storage, we're using Lustre, and we're getting about 50 gigabytes per second. And we're using Spark 352. So this is kind of the glossy brochure. The NVL 72 is one of these Grace-Blackwell nodes. It's got a ton of 72 B200s on it, 36 Graces. So we obviously weren't using this whole machine in the benchmark. We were only using 8. But it's got full NVLink between the B200s and the interconnect between Grace and Blackwell, like Clemens had mentioned. Okay, so I'm going to dive into one of the interesting components. So with all this hardware and NVLinks, we can really take advantage of it in what's called the Spark Shuffle. So it's a phase where you're transferring data between the maps and reduced sides. And so Spark has a shuffle manager in it. We have a custom shuffle manager called the Rapid Shuffle Manager. And you can set it up in 2 different modes. So we have the multi-threaded mode. And this is for if you don't have any fancy hardware, NVLink or anything like that. You can just use this and it will still accelerate shuffles. Then the UCX mode is UCX is an open source component that you can go download, and it can take advantage of the NVLink or InfiniBand or Rocky, and it's actually smart enough to use what it thinks is the most efficient one if you have them multiple set up. And under the covers, the UCX layer is what's end up calling into CUDA for like NVLink. So Grace-Blackwell would use NVLink. So looking a little bit more here at the shuffle manager. So this is the multi-threaded mode. So you have a task computing data, and normally at the end of it on Spark, it writes that data to disk. And our multi-threaded mode also writes to disk, but it will do it in parallel with multiple threads. So normal Spark would do all this serially. So you'd get a serialized compressed write, and so forth. The multi-threaded mode lets you do this in parallel. And that serialize and compress is really expensive. So this can make a big difference in how long this takes. We also have the advantage of we're processing on the GPU, so a lot of times we'll have idle CPU cycles to where we can really, this can be efficient and not block the actual data processing. Okay, so what does this look like when we actually run a benchmark? So this is the configuration we used. So on the CPU side, some interesting things is executors, we have 32 cores per executor. We used all the cores on the nodes, so you'll see the shuffle partitions there is 1,792. This is basically to make that shuffle most efficient on the CPU side. We used all the processors. You'll also notice that the executor memory is 256 gigs, so that's heap memory, and since we're on the CPU, we use a lot of heap. If you compare that to the GB200 using the multi-threaded shuffle here, some of the major differences are, so we use 16 cores per executor. That's 1 GB200 per executor, basically. Our heap size is smaller because we're doing more off heap and using GPU memory for things. We just left the shuffle partitions at the 200, which is the default for Spark. The Spark plugins is where you actually enable our Spark Rapids plugin. The max partition bytes here is we're reading a little bit more data from our input. So if you're reading from Parquet, because the GPU really likes bigger batches, and so we can get more efficiency out of reading using bigger batches. So the pin pool is a very fast memory pool for transferring data between CPU and GPU. So we configured that at 128 gigs. And then we have spill storage size at 200 gigs. So basically, if we can keep any spills in memory, that's more efficient. The concurrent GPU tasks is how many tasks can actually run on the GPU at once. So here we have 16 cores on an executor. That means that you can run 16 normal tasks. And those can all be starting up and processing data, but then when it goes to run a GPU operation, the concurrent GPU tasks will limit it. And mostly that's because there's a limited amount of memory on the GPU. And so we start out with this static config, and we've actually added more logic to make that more dynamic, so you don't have to tune this as much. So then the shuffle manager here is enabled, and then we configure the shuffle manager to have 32 threads. So there's more configuration here. We're working on making that easier for users so you don't have to configure all these, but this is what we used for this benchmark. Okay, so our results. So the CPU versus the GB200 using the multi-threaded shuffle. We ran it with 3 different data sizes. So we have 3 terabytes, 30 terabytes, and 100 terabytes. At 3 terabytes, we had 3.5x speed up. 30 terabytes, we had 5x speed up. And at 100 terabytes, we had a 5.3x speed up. So you notice this is pretty linear. Both the CPU and GPU side were pretty linear speed up. Okay, so now let's look at the UCX shuffle. So both Spark Shuffle and our multi-threaded shuffle write to disk between the stages. So here, when our tasks runs and goes to write data, we have a spill framework. And basically, this is a caching framework. So it knows how to, or it will try to keep things in memory when possible. So it can cache things in GPU memory. If it won't fit there, it'll fall back to CPU memory. And then finally, if it won't fit there, it'll write to disk. Obviously, we want to try to not to write to disk because that has more overhead. And so on the right side, that's the executor 1, where we're actually doing a map and writing the data. It'll write to this spill framework. When that finishes, the next stage over here on executor 2 shows that reader will go through and try to pull the data. What happens then is we end up copying the data from the spill framework into a GPU buffer, copy buffer, and then it goes across UCX, and in Grace-Blackwell case, it'll use NVLink over to a GPU buffer on the other side, and then the task will read it right from that GPU buffer. So it's a very fast path. We don't hit disk at all, and we get a lot of efficiency out of that. Okay, so the configuration we used for the benchmark here, so it's a lot like the previous one where we enable the plugin. We have the same number of cores. Again, heap size is smaller. Here we did tune the shuffle partitions a little bit for the 100 terabyte. It was such large data, we tried to keep it smaller per task, so we configured that to have more partitions to split it more. Similar sizes in pin pool size. The spill storage, again, we increased at the 100 terabyte level to try to keep from writing to disk to keep it most efficient. Shuffle manager is the same. And then the other thing here is the shuffle mode. So we changed it to be UCX instead of the multi-threaded shuffle. And then UCX has this other parameter we had to set basically because we were using Java to disable some error signals. Okay, our results here. So this is comparing the CPU versus the GB200 with multi-threaded to GB200 with NVLink. So at the 3 terabyte scale, we went from 3.5x speed up to 4.1. At the 30 terabyte scale, we went from 5x speed up to 6.5x. And then at the 100 terabyte scale, we went from 5.3x to 5.5x. So you'll notice the 100 terabyte wasn't quite as good, didn't linearly scale. That's because we ended up having to spill to disk. And we're actively working on that to make that better. But this kind of shows how NVLink and that fast transfer can really make a difference. To look at that a little closer, so here are some of the queries at the 30 terabyte scale that shuffled a lot. So some of these are shuffling 1 terabyte of data. You can see that some of them got up to like 3x faster. I think the query 23 here, part 1 and part 2, can really show that. So it can make a big difference having that fast NVLink to there to transfer data. Okay, so what if you don't have a Grace-Blackwell in the newer hardware yet? So this is just a quick benchmark to show you how Spark Rapids could help you now. So this is running NDS and EC2 at a 10 terabyte scale. And here on the CPU side, we used 8 M7 GD 8 extra large. On the GPU side, we used G6 8x large nodes, 8 of them again. And we used S3 for storage. So our NDS data at 10 and we're only using 10 terabytes in this case, but it was stored in S3, and we're using Spark 351. The configuration is kind of similar to before. So obviously change the size of things based on the nodes we used. So we have 16 executor cores on the CPU side, and the executor memory is 32 gigs of heap. On the GPU side, again, we have 8 executors, so 16 cores, each one using, it was an L4, is what it's using. We enable the plugin, partitions are the same. We have a pin pool size, again, that's the fast memory to use to transfer data. And 32 gigs of spill storage. Here we're only using 3 concurrent GPU tasks because the L4 has a lot less memory than the B200. And again, we enable the shuffle manager. And so our results here, excuse me. So this is the 10 terabyte scale. So overall, we got a 4.6x speed up. Again, this is on EC2 nodes running Spark standalone. But it shows you what you can get now. And a lot of people, the L4s are a lot less expensive, and they're more available than some of the bigger GPUs. Okay, so you can go try this out yourself if you want. So here's some links to the Spark Rapids documentation. There's, excuse me. There's a collab notebook you can go try. And then we have documentation on our user tools. Those tools can be used to help you decide if your workload's a good fit for the GPU. There's also tools on tuning and getting started and debugging there. And that's all I had.